complex conjugate. And integrating a function times its complex conjugate, that often gives you a measure of total energy or power.
So the left side is like the total energy calculated in the time domain.
Yep,
And the right side is the total energy calculated using the Fourier transform in the frequency domain.
precisely. What Parseval's tells us is that the total energy, or technically the integrated squared magnitude of a signal, is proportional to the total energy of its Fourier transform. It's conserved, in a sense.
So it's like a conservation principle. Transforming doesn't create or destroy this total amount of the signal. It just redistributes it, from being spread across time to being spread across frequencies.
That's a really good way to think about it. The source does add that little note. If pi is normalized as on page 21, this means the exact factor, that 12, depends on the specific conventions used for the transform definition. But the core idea, the conservation, holds true.
Okay, so far we've mostly talked about functions of time, one dimension, but things exist in space too, right? Like images, fields, and physics. How do Fourier transforms handle that?
Oh, absolutely. They extend very naturally to multiple dimensions. Instead of time t, we use a position vector. Let's call it Could be 2D, could be 3D. And instead of angular frequency, we use a wave vector, k.
Okay, so if I have, say, an image that's 2D and I want to see its spatial frequencies, what does that transform look like?
The general 2D form, VBK, for a function, VR, is an integral over a little area element, dr. You integrate VR times e to the power of minus ik dot r dash ipor, where kr is the dot product of the wave vector and the position vector.
Got it. Dot product. And the source mentioned a simplification if the function has a certain symmetry, azimuthal symmetry.
Exactly. If v only depends on the distance from the origin, r not the angle. That 2D integral simplifies quite nicely. It becomes an integral just over radius, r from 0 to infinity, of 2 bar times vr times j0 part r. That j0 part r is a Bessel function. It pops up naturally in problems with circular symmetry.
Interesting. Bessel functions. Okay. And for 3D, like analyzing a potential field in space.
Same idea, just extended. The general 3D transform VBRK is the integral over a volume element, d Cordo, and you integrate VR times e to the minus ik dot r dash ir.
And I bet there's a symmetry simplification for 3D too. Spherical symmetry.
You bet. If VR only depends on the distance from the origin, the magnitude of r that 3D integral boils down to 4 divided by k times the integral from 0 to infinity of VR times r times sin dot r. This form is super useful in physics, things like scattering problems, potentials from spherically symmetric sources, things like that.
And the source also gives a way back, right? The inverse 3D transform from k-space back to VR.
Yep, it shows VR is 1 over 2 cubed times the integral over d quarts, all of k space of vbk, times e to the plus ik dot r. ITR. You see that symmetry again between forward and inverse, just with a sign change in the exponent and that scaling factor?
Okay, the source then gives us some concrete 3D examples, and crucially, properties about derivatives. Let's look at the specific transform pairs first.
Right, these are really key examples, especially in physics. First one, VR equals 1, 4 pi r, like a basic point charge potential. That transforms to VBIK equals 1 kr. Very simple form in k-space.
1 over 4 pi r becomes 1 over k squared, okay? And the second example, it looks similar but with an extra term.
It does. It's VR equals e to the minus lambda r divided by 4 pi r. That transforms to VBOK equals 1 kr plus lambda. That ER term is an exponential decay. Lambda controls how fast it drops off. This pops up in things like the Yukawa potential or screened Coulomb potential in plasmas, where the interaction weakens faster than 1r.
Okay, those are useful pairs to know. But now the derivative properties you mentioned, this is where things get really powerful for solving equations.
Absolutely. Think about operators like the gradient, showing direction of change, dot or the Laplacian, which shows up in diffusion, wave equations, all sorts of places. These can make equations hard to solve directly in space.
Right, calculus with multiple variable. So what does the Fourier transform do to these operators?
Here's the magic trick, like we saw with convolution. The source says the gradient, dvrk, transforms to just I times k times vbfk.
Wow, okay, the gradient operator becomes multiplication by Ike. What about the Laplacian?
That transforms to minus k squared times vbik. So minus k vbik.
So differentiation in space, these potentially complex operations, just become multiplying by factors of k in the frequency domain.
Exactly. The gradient ek becomes multiplication by the vector ik. The Laplacian ek becomes multiplication by the scalar negus k. This is probably the major reason Fourier transforms are so critical for solving linear partial differential equations. You transform the whole equation, differential